Let's take a look at the graphs of sine and cosine when we treat the angle measurements as the input. This will be different than when we looked at the x and the y as being points on a terminal ray and that circular graph that we created. In this case, the angle is the input and the ratio is going to be the output. The parent functions of sine and cosine are periodic functions with an amplitude of 1 and a period of 2 pi. All right, so what is a periodic function? A periodic function is a function whose graph has a very repetitive process to it. What that means is that if you were to grab one chunk of the graph, you choose wisely one chunk of the graph, you could literally tack it onto itself forever and it creates that graph. Hence the repetition that we see there. All right, the period of the graph, the period, for sine and cosine it's 2 pi, but the period of the graph is the width of that section that you would need to take to repeat the process. So it's the width of the graph until it begins repeating the same process. The amplitude is going to be defined as half of the distance from the highest point to the lowest point. And it's sort of a weird way to talk about stuff. Why not just talk about it as how far is it from the highest point to the lowest part? Okay, but when we see the graphs of sine and cosine, it's going to make more sense that the amplitude is half of the distance from the highest point to the lowest point. And in this case, it's going to be 1. You're going to notice that in my blank template here for the graphs that I do have 1 and -1 marked off on my grid. And that's going to have to do with the amplitude. Okay, the full distance between these values is 2. So half of that distance is going to be 1, and that's what we're talking about with the amplitude here. As mentioned before, the inputs for the sine and cosine functions will be angle measurements. So if you look at the x-axis, you're going to notice that I got them marked off at pi over 2, got pi, 3 pi over 2, and 2 pi. So these are all angle measurements. So we've got, these are in radians. It is perfectly acceptable to think of them as degrees. That would be 90 degrees, that would be 180, 270, and 360. And it might even help out when you start to try and break down these parts here, because you could look at that as 30 degrees, 60 degrees, and then 90 degrees. Okay, so I do have it written in terms of radians, but you can think of them in degrees if you want. All right, so how to graph this? Okay, so the functions are simply this. It would just be y is equal to the sine of x. The input, which we're calling x here, is really an angle measurement. The output is going to be the y, so that'd be the height at which you plot the point here. Okay, so what we need to do is take a bunch of angles, put them into the sine function, and then once we have enough dots, start to connect them and get an image. Now remember that we know our special angle measurements. Okay, we know our special angle measurements. So let's recall those. Actually, go ahead and just get this out for a second here. For sine, at 0 degrees, we have 0. At 30 degrees, we got 1/2. 45 degrees is going to be square root 2 over 2, which might not be as easy to graph that on the chart there unless you evaluate it as a decimal. Same thing with 60 degrees, you got square root 3 over 2, and 90 degrees is going to be at 1. Okay, so let's go ahead and plot what we can there. 45, I actually don't have a marking for it, it'd be sitting right there. Okay, but the sine of 0 is 0. The sine of 30 degrees, which would be here, is going to be at 1/2. So put a little dot there. At 60 degrees, we got square root 3 over 2. Let's take a look at what that is. The square root of 3 divided by 2 is going to be 0.866. So it's actually pretty close to the top. Okay. And of course, I'm going to add one more before I plot that one. At 90 degrees, the sine of 90 is at 1. Okay, it's going to be right there. All right, this dot, that would be at 0.5, and that's at 1 whole. It's going to be a little bit closer to the top end. So I'm just going to estimate that it's about that location. And if we do this right, you're going to notice that they're not a straight line. You actually have somewhat of a curved shape to get to there. All right, and there you are. Those are our special angles. So how is that going to graph this whole thing for us? How are we going to get all the way out to 2 pi? Well, we got reference angles. Okay, remember that we have reference angles and that anything with the same reference angle is going to get evaluated as the same. Okay, so let's talk about 30 degrees for just a sec. Do a real quick sketch here. All right, at 30 degrees, there's other angles that use that as a reference. Over here in quadrant 2, that would be at 150. Quadrant 3, that would be at 210. And then over here in quadrant 4, that would be at 330. Okay, so at all of those values, we can actually plot a 1/2. Except sine is positive in the top and negative in the bottom. Okay, so at 150, and these are all increments of 30 here, so that's 90, that'd be 20, 120 that is, and then 150. You're gonna get half right there. Actually, at pi is right between the positive and the negative, so that's gonna give you 0. 210, 30 degrees over, you're gonna be at 0.5. At 270, right between the two negatives, that actually gives you -1. And at 330, which will be way over here, that'll be at a 0.5. And then at 2 pi, that's the same thing as 0. That's gonna be here. And now, I think we don't need to mark off the rest of the dots. I think we can figure out what the graph is gonna do here. It's actually gonna curve back down. It's gonna mimic that side. And then the bottom is gonna look the same, but just on the bottom side there. And that is what we call one period of the sine function. Okay, beyond here, it just begins to repeat itself, because once you get to 360 degrees or 2 pi, you basically start over. You start the whole cycle again. So you're gonna go up and then you'll go back around. Okay, so I'm gonna go ahead and add more to the graph here. In this direction, you're gonna end up going down, be back at that spot, high point here, over there. And that is gonna be about the best that I can actually draw that graph. And that is your parent function for sine. The parent function for cosine pretty much looks exactly like the graph that we have for sine, except that it's gonna be shifted to the side a little bit. And I think it's helpful just to go ahead and let you know that from the beginning. That way we don't have to spend as much time plotting points. Now the reason that that is, or at least a reason we can start to justify that that could be true, is when we look at the values that we had for the special angles, these values are the same values that we got for sine. They're just in different places. Okay, so for cosine, at 0 degrees, you're actually gonna be at 1, where the sine function started at 0. But then at 90 degrees, it's gonna flip-flop and cosine is gonna be at 0. Okay, so all of these values, they're pretty much the same thing, which means that the graph is gonna look pretty close. As I just mentioned there, the cosine of 0 degrees is actually at 1. The cosine of 0 degrees is at 1, and the cosine of 90 degrees is at 0. Okay, so in the sine curve, it went sort of an upward direction here, but we can see that we're moving that way. All right, other little checkpoints here. The cosine of 30 degrees, is gonna be that square root 3/2, which was that 0.866, so on. And we'll go ahead and take a look at this one too. The cosine of 60 is at 1/2. That'll be one that I'll use a lot. Okay, so at 60 degrees, we're at 1/2. And at 30 degrees, we're a little bit higher up. We're a little bit higher up here than maybe the halfway mark there. Okay, so that's gonna give you that curve shape over here that we did see in sine, just located in a different location. All right, and then let's go ahead and take a look at this picture again with the positives on the right, negatives on the left for cosine. Directly between two positives is gonna be at a height of 1. Okay, so that was at 0 degrees, and we just saw that one right there, so at 1. That will also happen at 360, which will be way over here. Directly between positive and negatives, you're gonna get zeros. Those are gonna be your intercepts. Okay, so at 90 and 270, there's one already at 90. 270 would be right there. And directly between the two negatives, you're gonna get a -1. So that'll be down in that spot. So if we treat this as the general shape throughout, you're gonna see it curve down into that spot here and there. So overall, it is the same shape. It's just positioned a little bit different. Now, it might look a little bit more different when I only show one period of it, But let's see, we're going to come back to that spot. We'll be at the bottom here, here, then here. Once we get a little bit more repetition in the graph, you'll see that it does have the same general shape, just shifted over a little bit. So there's the sine curve. We have a high point here, so that'd be like your cosine. You see that part there. Okay, your general period for a sine is that. You can see it here. You can see it there in the cosine function. Next, what we're going to do is look at how we can perform transformations onto the parent functions of sine and cosine. Now, back in Algebra 2, you had looked at a ton of different functions, and for each of those functions, when you were graphing them, we talked about how you could stretch the graphs either vertically or horizontally, how you could compress the graphs, how you could flip the graphs, and even how you can shift the graph to different places, whether you shift up and down or left and right. Okay, now all of those things, you can do that with the trig functions as well. So here's what the trig functions look like with all the possible values that we could add to the function in order to transform it. Okay, now the basic function for each of these would just simply say y equals the sine of x. That's all it would be. Y equals the sine of x. This would be y equals the cosine of x, where you simply have an input that goes into your trig function. Okay, so all of these variables are extra things. You've got a d value, you've got an a value, b, and a c. All right, now the d value, we'll just go left to right here. The d value is something that is being added onto the rest of the function. That's all it does there, just adds onto it. If it is something that you'd want to subtract from it, you just put a negative in the front of it. We typically do put the d in the front because if you put it in the back, it sometimes just gets sort of mixed up with the things that are in the sign. So you should have parentheses, but just for the sake of organization, we've moved that one to the front. The a value is something that you are multiplying by the function. You're going to multiply it by the function. Inside the function here, you've got bx minus c. The b is a value that you directly multiply to your input. Okay, so that happens before the sine or the cosine. We also have some adding or subtracting that we can do before the sine function. So all that happens within the sine function to the x, and then you do the trig part. You then multiply by a value of a, and then at the end you can add or subtract to that. All right, so what do all these pieces actually do? The a value, that factor, is going to change the amplitude. We would say that the absolute value of a is the amplitude. Okay, now if a is a negative value, it is going to flip the graph, and you would have seen that with other functions in the past. Okay, it would flip it, but the absolute value, the a, is what we call the amplitude. So if you're asked a question about what would be the amplitude of this graph, it's just the positive version of whatever number would be there. All right, you can also think of that as just stretching the graph vertically. The period, all right, so we have an amplitude to these types of graphs. We also have a period to a periodic function, and the period to the parent functions is going to be 2 pi. Okay, so if you have a b value that's 1, like you didn't even write anything there, 1, 2 pi divided by 1 is still going to be 2 pi, and that would be your normal period. But if you have a value that is in front of the x, or a value that's being multiplied by the x, you need to divide that into the 2 pi, and then that'll give you the correct period. That would be the width of the graph, the width of one of those sections. All right, phase shifting. That would be a new term there. Phase shifting is talking about moving left and right, moving it left and right. For that, you would have to take the c value and divide it by the b value. Now, let me bring up a point here that's really important, but is also really confusing. These equations have a minus c in here. So what that means is that the way that you see this value in the equation is the opposite of how you would expect it to move in the actual graph. Okay, so if we actually subtract a number here, like we had a minus pi, what that would tell us is that we're shifting to the right. You'd be shifting to the right pi units if it said minus pi. If it said plus pi, you have to actually think of that as a negative pi, which would tell you that it's shifting more to the left direction. In addition, there is a b value. So if you have a b value, you do need to make sure that you divide it into the c to get the appropriate shift. If the b value is 1, it doesn't really do anything there. All right, last, the d value, that is the easiest of all of these. It is the very last part to the function. Everything else has happened, and then you've got this d value that you either add or subtract. And that will be your vertical shift. Make sure that you do that one last. It's a lot easier if you do that last. In fact, it's a lot easier if you work from the inside out. Start to figure out what these do to the graph. Once you do that, and you can maybe draw the graph in stages, do that, then stretch it, flip it, whatever the a value is going to do here, and then last, do the d part. Work from the inside out. For the first couple examples, I'm only going to do one transformation. Once we start doing multiple transformations, it does start to get more complicated. And I think it has something to do with the fact that these are periodic functions. There's just something about that repetitive nature in the graph that makes it a lot harder to do multiple transformations. Okay, so we will do some examples where we do have multiple transformations, but the first couple are going to start out with just single things that we can pinpoint. For example, number one, the parent function of sine would just simply say y equals sine x. That's all it would be. So the only thing that we've added in here is the 2. Okay, now that 2 is going to best fit as an a value here. It's going to best fit as an a value. So we're looking at changing the amplitude to this graph. In other words, what we're going to be doing is a vertical stretch to the graph. In this case, it is going to be a stretch because it's a value greater than 1. If you had some fractional number like 1/2 or 1/3, that would actually be a compression. So that's the only thing that's going to be changing here. In order to work with these graphs and not making it as complicated as it could be, we're going to focus on key parts of the graphs. Remember that it does have a repetitive shape to it. Okay, it has a very repetitive shape to it. So we're going to choose to look at intercepts. That would be like x-intercepts. We're going to choose to look at the maximum points and the minimum points and use those points, which in this case here, just in the parent function, one period of the parent function, you actually have 5 points. You got one here, 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 and then you've got the high and the low. Okay, so between those 5 points, we should be able to get a pretty good look at what happens in the graph. So this picture is sine x. It's sine x. It's already been created by taking all the different values of the angles for x and then putting it through sine. The 2, after the fact, is going to multiply all the outputs that we get from here. It's going to multiply all the outputs that we get from here by a factor of 2. For example, this point in the original function at 90 degrees or pi over 2, that has an output of 1. So it's going to magnify it up to here. Likewise, this point over here, that low point, which is -1 down, that's also at 270 or 3 pi over 2, that point being at -1 is going to get magnified by 2. You're going to multiply by 2 and it ends up down here at -2. Okay, so these points have stretched out vertically to those locations. And now every single point along the graph is going to stretch by a factor of 2 away from the x-axis because that's where the y values are 0. So it's going to stretch from there. If you have a point that is on the x-axis like this, this, and that, those points don't move anywhere because if you multiply 0, the sine of 0 is 0. If you multiply 0 by 0, you're still at 0. Or at the sine of 180, the sine of 180 is 0. So if I multiply that by 2, I'm still at 0. I'm still there. Okay, so all the other points are going to stay where they're at. And what we can do from here is just make a general curve that goes through these points. In example number 2, we have another sine function. And in this one, we have the x value being divided by 2. Okay, so it's happening here. So nothing out front. This is actually happening inside of the function. All right, so I'm going to go back up to the general template and see what this best fits. Obviously, it's not D. It's not going to be A because it's not outside. It's going to be here. Since that 2 is not being subtracted or added to it, that means that that 2 is the B value in some sense. And the B value, though it does contribute to a phase shift when there's a C value, the B value is mostly about changing the period of the graph. Okay, so it's going to horizontally either stretch or compress it. Okay, so what exactly is the B value here? We need to interpret that x over 2 is the same thing as 1/2 multiplied by 2. So that means that our B value is 1/2. Now, to figure out what our new period is, we're going to take 2 pi, let's say p equals, we're going to take 2 pi and we're going to divide it by 1/2. Okay, so now we got to think about how do we divide by fractions. Okay, there's a general rule which that I refer to as keep change flip. You can do 2 pi over 1, multiply that by the reciprocal of the denominator, which is 2 over 1. So the ones don't matter. We get 4 pi. Okay, so the period of this graph is now going to be 4 pi. It's actually going to be stretched out. Originally, that b value, we see it as a fraction, which if that were an amplitude type number, if that was an a value, that would compress it vertically. Okay, but what it's going to do here, because of the way that we had to divide it, it actually becomes a horizontal stretch here. Okay, so the original period goes out to 2 pi. So this is going to be 1/2 pi. That would be pi, 3/4 pi, and then 2 pi. Go ahead and add that in there. That would be 2 pi at that spot. So the whole graph, well, this isn't the whole graph because it goes on forever, but this whole section of the graph is now going to need to consume 4 pi. Okay, so that's 2 pi, which means that this would be 3 pi, and then way out here is going to be 4 pi. So this one's going to be a tough one to draw because it's going to be so stretched out. It's going to look pretty darn flat here. All right, not only does that endpoint that I looked at go all the way out here to 4 pi, but if we look at a comparison between these two, what I've ended up doing is doubling. That's what ended up happening here, is that I doubled the whole graph. So if I take any of the distances that the main parts of the parent function are from the y-axis, if I take the distance that any of the regular points are from the y-axis, like this point right here is pi units away. If I take that and I double it, just like this part was doubled, okay, that'll take me to here. That will be correct. Okay, and now I can take this maximum point. I can take that, which is 1/2 a pi away, double it. That'll get me here. And then that one, it might be easier in this picture, just count it as, there's these large boxes, so I got 1, 2, 3. Just double that, so another 1, 2, and 3. Which I ended up in the wrong spot now. All right, so 1, 2, 3, 1, 2, 3. Okay, it's going to end up right there. And to the best of our ability, we're going to connect these. It's going to be tough. It's going to be tough. They're so far apart here. All right, and that's about as good as I'm going to get that graph there. All right, for example number 3, we're going to look at 2 transformations. Okay, and you're going to see inside the parentheses, we have a b value and we also have a c value. So everything's going to happen inside of here. We don't have an a value and we don't have a d value, so we're not going to have any vertical shifting from the d value, and we're not going to have any vertical stretching or flipping from the a value. We just have a b and a c. All right, now the b value, we've already talked about what that one does. We've talked about that because the b value by itself without the c, the b value is going to change the period. Okay, so we have a b value that's equal to 2. So if we want to figure out our new period, we take 2 pi and we divide it by the b value, which is 2. Okay, so that is going to just cancel out the 2's, and the period ends up being pi. That'll be our whole period here. So this case, it's actually compressed it. Remember that the original period is 2 pi. The original period is 2 pi. So this is going to squish the graph and make that whole curvature here. Oh, and by the way, we are looking at cosine. Okay, the graph looks a little bit different. This is the parent function of cosine. It's going to squish that whole graph within here to here. That would be pi, right? Whole thing's 2 pi, so that would be pi. Now, what I'm going to go ahead and do is just take care of that one part. I'm just going to go ahead and compress it so I can get a look at that. And then afterwards, I'll think about what the c value is going to do, which is the phase shifting part of it. So sometimes what it's good to do is just one transformation at a time. All right, so the whole graph is going to get compressed to just pi. So you have the high point there at the y-axis. Your next high point is going to be here at pi. Your low point, instead of being at pi, is going to get pulled in to here. Your intercepts are going to be at 1/4 pi and 3/4 pi. They'll be at those spots. And what I'm going to do is just dot this one because I want to indicate that that one is not the final answer. But I want to have an idea of like how that's going to be compressed. All right, so next let's talk about the C value here. All right, so the C value is not pi. It is actually, the C value is actually negative pi. And that turns out to be a little bit of a tricky thing here, but these equations, whether it's what we're doing here or if you look at this in quadratics or something else, the general template has a negative in there. You want to train yourself to think that whatever you see in the equation is the opposite because it needs to be a minus C. Okay, now R says plus pi. So the only way that I can make plus pi look like a minus is if I do a minus negative pi. So your C value is actually going to be the opposite of what you see here. Okay, so C is a negative pi, and that's important because we're going to be shifting left or right. Okay, and if you get the sign backwards, then you go the wrong direction. All right, the actual phase shift. The phase shift. That is going to be equal to the C value divided by the B value, which for this would be negative pi, divided by 2. So if earlier we were really careful about switching that sign here, which we did and made sure that we had a negative pi, this actually tells us how far we should move the graph to the left. Okay, so we're going to take this graph, the one that's been dotted, because that is our compressed graph. That's really how the shape should look. We're going to take that graph and we're going to move everything to the left, pi over 2 units, which would be the same things like 90 degrees. All right, so in the general graph that I had here, I'm going to go back to the original, just make sure I scale things out. That is 2 pi. Okay, so this right here is pi. That means that this is half of a pi. So I'm going to be moving it that amount of space. Okay, so that high point is going to end up here. This intercept is going to end up here. Low point is going to be here. That intercept is going to be on top of that one. And this high point is going to be there. And I'm going to go ahead and mimic that shape using these points. All right, and that is our graph, or at least it's one piece of our graph. What we're now going to do, since we're at the final stages of it, we're going to go ahead and keep making some dots here. Make sure I can see them. And go ahead and connect and get a little bit more from this. So you can do the transformations with, you can start with just one period, and then once you've got that one period locked into its spot, you can just build the rest of the graph around it. For example 4, we're going to be looking at a cosine function again, but for this, we're going to be doing 2 transformations, and they are a period change and also a vertical translation. Those would be the 2 things that we'll be doing. The vertical translation is this part out here. It is that value that's being added to the rest of it. It happens at the very end of the function. That is the very last part. Once we tackle this, we can just elevate the whole graph by 2 units. That's all we got to do with that. All right, so working from the inside out, we're going to take care of that 4 first. All right, now that 4 being a factor that is right next to the x, that means that we have a b value. That would be a 4. Okay, and now we're going to take 2 pi, the original period of the graph, divide that by 4. Let's see, that's going to reduce down to pi over 2. Reduces down to pi over 2. So the period of this graph is going to be pi over 2. That is actually a 1/4 of the size. I mean, you can see it right there. It's a 1/4 of the size of the original graph. So from here to there is 2 pi. That means that the entire curve has to fit within that space. It's going to be a tiny little graph tucked in there real tight. You're really going to look at the distance that all of our intercepts and our max and minimums are from the y-axis. Okay, so that point being on the y-axis just stays there. This point is going to have to move all the way in to here. That low point is going to move to here. It's going to be half of what our period is. That was a halfway point to the original, so it's halfway for that one. This point is going to be here, and then that high point is going to be at pi over 2. Okay, so this is our graph. This is going to be hard to draw. All right, tight little graph. Trying not to make it just look like a V shape. Right there, give it a little bit of a curvature. All right, so that is the size of our graph as far as like width is concerned. All right, now in addition to that, we have the transformation of the vertical translation. That plus 2 is just going to take all the outputs that we have, an output of 1, output of 0, output of 0, output of negative 1, 1, and we're just going to increase all of those by 2. Okay, super easy. Take the 1, put it up here at 3. Take the 1, put it up at 3. Negative 1 is going to go by 2. That will put you right here, which is pretty nice because now the graphs won't be on top of each other. This point will be here. That point will be there. All right, and this is, again, pretty difficult to draw here because it's so tight, but that is going to be one period of the correct answer of this graph here. Okay, now what we should do is go ahead and keep adding some dots here. Yeah, that should be, well, it's all of them I can do. All right, I'm going to try and take my time here and not rush it. All right, that would be our graph. That should be the graph of this guy.
Later, blah.